Combustion reactions. Oh, it's coming back to me now. At the beginning of that section on redox reactions, we said that reaction with oxygen was a very common redox reaction. Combustion reactions involve something reacting with oxygen. And it's going to form one or more oxygen-containing compounds. Often water is involved in there. Another feature of combustion reactions is that they emit heat. They're exothermic. And why do we burn propane in the gas grill in the backyard? To chill our food? No, to heat it, right? Combustion is useful to us because it emits heat. So natural gas is predominantly methane, which is CH4. It reacts with oxygen in this way to form CO2 and H2O. And if we look at the oxidation states here, here's two nonmetals, and so we go through the list, fluorine, hydrogen. Oh, hydrogen. Hydrogen gets to be number 1. So we've got 4 plus 1 things there, and so carbon must be minus 4. Here, oxygen element is 0. Here, carbon dioxide, oxygen gets to be minus 2. So carbon has to be plus 4. And over here we have water. Hydrogen gets to be plus 1, and oxygen gets to be minus 2. They're both happy about that. What happened to the carbon? Its oxidation state went up. It was oxidized. When carbon's oxidized, it's often combined with oxygen. The term oxidation actually comes from organic chemistry. In organic chemistry, we mostly think of oxidation as increasing the number of carbon-oxygen bonds. So that makes a little more sense than the whole thing with the electrons. But you're not in organic chemistry yet. So the carbon got oxidized. The oxygen got reduced. Its oxidation number went down. And hydrogen stayed the same. Sometimes you just have to stop and think about it because it's so easy to get backwards. Any questions? Ethanol, that's the alcohol in alcoholic beverages. Reacts with oxygen in a combustion reaction to form carbon dioxide and water. There's no question. Where's the question? It's just telling us. I guess it's just telling us, oh, look at that. Some of these slides were created very late at night. Just for grins, let's look at the oxidation numbers. We'll start with something easy. How about oxygen? 0. Okay, here's the ethanol. Hydrogen gets to be plus 1. And oxygen is next. He gets to be negative 2. Carbon has to suck it up and take what's left. So this one's a little complicated here. We've got 6 hydrogens, 6 times 1, and we've got 1 oxygen. That's a negative 2. And then we have 2 carbons, so we'll call that 2x. And that adds up to 0 because it's compound. So we have 6 minus 2, that would be plus 4, right? 4 plus 2x equals 0. X must equal negative 2. Right? So in here, I'll just write them down there, minus 2. And this was minus 2, and this was plus 1. These guys are the same as they were on the previous slide. The oxygens are minus 2, the hydrogen is plus 1, and this carbon is minus 4. Sorry, yes, thank you, plus 4. Just missed the little vertical line. So what's getting oxidized? Oxidation is loss of electrons. It means that the oxidation state goes up. So which one has an oxidation state that's going up? Carbon. From -2 to +4. So carbon's being oxidized, and something must be being reduced. What's being reduced? The oxygen here. This one isn't having anything happen to it, but the elemental oxygen here is going from 0 to -2. Yes?
The oxidation state for just the free element, just like oxygen, I thought it would be equal to its charge.
Well, let's see what would happen. So if oxygen here always wants to be -2, could it be -2? We also have to have the oxidation states add up to the charge on the whole thing. And this guy doesn't have a charge, does he? So the only way we can have them add up to 0 is for them to be 0. Okay? So we have those rules, and at first you just have to go through the rules. After a while, you just kind of get a feeling for it, and then it becomes a little bit easier. Does anybody else have any questions? Write a balanced equation for the combustion of benzene. This is something that you definitely need to be able to do. A combustion reaction for something with carbon and hydrogen, or carbon, hydrogen, and oxygen, it's reacting with oxygen. It always forms CO2 and H2O. So we've got C6H6 plus oxygen, and that's going to form CO2 plus H2O. Then we have to balance it. So over here I have 6 carbons. I'm going to go over here and I need to put a 6 in front of the carbon dioxide. Over here I have 6 hydrogens. Over here each water molecule has 2. That tells me I need 3 water molecules. Oxygen is by himself as an element. It's best to leave him for last, because we can adjust this one without messing up everybody else. So on the right side, in the products, we have 2 times 6, we have 12 oxygens there, and we have 3 oxygens here, and that equals 15. But you can only buy pairs of oxygen. And so how do we get 15, which is an odd number, out of pairs? Well, you can use a fraction. What fraction would give us 15? How about 15 halves? Now, is that a beautiful balanced equation? No. We would have to take this denominator and multiply everything to clear that fraction. So I'll tell you what most students seem to prefer. We look at this, we have an odd number on this side, and we have an even number here. And so we have an odd-even problem. And these pop up a lot in these combustion reactions. This is where we most commonly see them. What happens to an odd number if you double it? It becomes an even number. So what we're going to do is we're going to double everything, except the oxygen, which we haven't given a number to. So we're going to double that, we're going to double this, and we're going to double that. Now, under CO2, we have 24 oxygens. Under water, we have 6 oxygens, and that gives us 30 oxygens on the right side, an even number. And so then we put a 15 in here. The same thing has been accomplished, but we didn't use a fraction, and most people seem to think that this way makes a little more sense. Any questions? Look at that. Okay, it must be here for a reason. Let's do it. Okay. Copper is obtained from sulfide ores, such as chalcocite, I don't know, copper 1 sulfide, I feel better about that, by a multi-step process. After grinding the ore, it's roasted, heated strongly with oxygen gas, to form powdered copper 1 oxide and gaseous sulfur dioxide. How many grams of oxygen are required to roast 100.0 grams of copper 1 sulfide? Anybody's head feel like it's going to explode? Wah! Okay, we can do this. This is a stoichiometry problem. They've given us names and talked about a reaction that's going on. They gave us an amount, and they're asking for an amount. It's stoichiometry. So the thing we need is a balanced chemical equation. So let's write that up at the top. What is one of the reactants? The copper 1 sulfide. So copper 1 is Cu plus, right? Plus 1 because that's what the Roman numeral means. Sulfide has what charge? 2 minus. So we need to identify the charges so that we can write the formula for copper 1 sulfide. So it's Cu2S. Plus, what's the other reactant? Oxygen. It's heated strongly with oxygen. So O2, because oxygen's a diatomic element, and this forms copper 1 oxide. So copper 1, again, is Cu plus, and oxide is O2 minus. So when we put those together, we get Cu2O. And gaseous sulfur dioxide. What's the formula for sulfur dioxide? SO2. Okay, I'm going to erase these because they're going to be in the way. Is this equation balanced? No. So 2 coppers, that's great. Sounds like 2 policemen. 1 sulfur and 1 sulfur, so that's fine. And then over here we've got 2 oxygens and 1 oxygen. We have a total of 3 oxygens on this side and 2 over here. It's another one of those odd even problems, isn't it? So let's double everything. Let's put a 2 here, and a 2 here, and a 2 here, and see if that helps. Copper is still balanced. 4 on each side now. 2 sulfurs, 2 sulfurs. Those are still fine. The oxygens now, we've got 2 in the copper 1 sulfide, and we've got 4 in the sulfur dioxide. Total of 6. So we need 3 of these guys. Okay? So again, those guys are in the way. Move them out. Erase them. There we have our balanced chemical equation. Now we look through here again. There's only one number in this problem. There's a lot of words, but only one problem. I mean, only one. It's only one problem. But I have other problems as well, don't I? 100 grams of what? Copper 1 sulfide. So I'm going to write 100.0 grams under the copper 1 sulfide. And what's the question? How many grams of oxygen? How many grams? Now, does this look like a more doable problem? This is stoichiometry. Grams to moles to moles to grams. It's not even any of those milliliters and molarity stuff, right? Grams of Cu2S to moles of Cu2S to moles of oxygen to grams of oxygen. (100 grams of Cu2S). We're going to have 3 factors in here. we're going to have moles of Cu2S. That's going to be divided by grams of Cu2S. And then we've got moles of oxygen, and that's going to be divided by moles of Cu2S. Because we're putting these in pairs like this so they cancel out. That's the whole big idea here. And then at the end, we've got grams of O2 per mole of O2. And those guys cancel out. Equation says 2 Cu2S and 3 oxygens. 3 oxygens, 2 copper, 1 sulfides. We need molar masses. Well, oxygen's easy. O2 is 2 times 16, 32. And copper, 63.55. 2 coppers, 63.55. And 1 sulfide, 1 sulfur, 32.07. I'm getting 159.17. Anybody else? Okay. So 1 mole of copper sulfide, 159.17. 100 divided by 159.17 times 3 divided by 2 times 32 equals. How many significant figures should this have? 4. 30.16 grams of oxygen. Pardon me? Why are we using O2? That's a good question. In this equation here, oxygen is an element. It's by itself. It's not in a compound. And when a diatomic element is alone, it forms molecules. It doesn't always do O2 when it's in a compound because it's not alone. It's okay being with 2 copper friends. But if you just have oxygen alone, it's going to pair up with another oxygen. So that's why it's O2. Any other questions? Now, was that as bad as it seemed at first? No. So some of these things are like that dog with the really loud bark. It's like, wow, that's really scary. But then if you look at it a little more and just start pulling it apart, it's really not that bad. Just a lot of words. A lot of words. Personally, I like numbers, but hooray!